Hi everybody, my name is Tommaso Cucinotta. I'm from the Real-Time Systems Laboratory of Scuola Superiore Sant'Anna, and I'm presenting you today an evaluation of adaptive partitioning of real-time workloads on Linux, a joint paper with my colleagues Luca Beni and Andrea Stevanato, and Daniel Cristode Oliveira from Red Hat. This research has been sponsored by the European Commission through the Horizon 2020 funding program within the Ampere European project. So in terms of background, this paper focuses on multi-core processing platforms, which, as we know, have been increasingly used in a number of application domains, which span across not only the traditional high-performance computing scenarios, but also the real-time and embedded systems scenarios, where we basically have kind of high-performance embedded needs. For example, for realizing intelligent real-time driving assistance, real-time video processing and object recognition, or time series forecasting. So these all require complex software stacks that benefit from a number of acceleration technologies, including multi-core, GPGPU, and FPGA. Also, we focus on open real-time systems, so where we may have real-time tasks dynamically entering and leaving the system at any time, and where we might have additional requirements, for example, minimizing energy consumption, etc. So the focus of the paper is the presentation of the adaptively partitioned EDF scheduler multi-cores, but as this scheduler had already been presented in the ACM SAC 2020 conference last year, we actually contribute in this paper a real implementation of the scheduler in the Linux kernel by modifying the scheddeadline code base, and we perform an extensive experimental evaluation comparing with the results obtained in that last year paper by simulation only. First of all, a few scheduling basics. So real-time tasks are scheduled using a custom bandwidth server algorithm, which ultimately schedules tasks by EDF. And in this, with this tool, each task with parameters classical worst case execution time, minimum intervariable period t, are attached a dedicated reservation with a reservation runtime q and the reservation period p, where normally you want q equals c and p equals t in order to not miss any deadlines. However, as the scheddeadline supports both a global EDF and partitioned and clustered EDF configurations, in order to actually not miss any deadline, you really have to use, for example, a partitioned EDF. So you have to partition the tasks from the user space, which can be easily done and arranged. Otherwise, scheddeadline by default uses global EDF. So as you know, this only gives you a tardiness bound. Also, the scheduler embeds in the kernel only a necessary admission test, which is checking whether the overall utilization is lower than or equal, and the number of cores, actually it's multiplied by 0.95 by default. This is because the complex admission tests with more complex timing parameters are all left to the user space. So APDF employs utilization-based heuristics for task and core assignment by realizing mainly the first fit heuristic, but also we realize the worst fit in the code base. So the FF is good for simple utilization-based overall test, and it's not so good for energy management, because when we scale frequencies using DBFS up and down, we need to migrate tasks in order to restore the first fit invariant. On the other hand, worst fit is good because it's spreading workload across cores, and allows generally for keeping lower DBFS frequencies, but it becomes bad when a task with a big utilization arrives, because in that case there might be no space for it on any of the cores. So we might need to migrate tasks to make room. In AP EDF, what we do is basically we enrich scheddeadline by adding a placement logic that employs the first fit or worst fit heuristics. And the placement logic is triggered at any real-time task arrival or wake up, and it follows three simple rules. So first of all, if a task is already on a core that is not overloaded, so a core where locally the Llewellyn Island test on the locally hosted reservations is satisfied, then the task is not moved ever. So on the other hand, if the local test is not satisfied, then we try to find a core where adding this task would not overload the core, and then we push the task to that core. And this search of the core is done by using either first-fit or worst-fit heuristics. On the other hand, if known such core exists where we can place safely a task, then we can fall back to global IDF. The general properties obtained this way are easily stated. So first of all, once a schedulable partition is found by this heuristic, then no more migrations are done on the tasks, contrarily to what Schedulability does. It keeps migrating tasks, as it will become evident from the experimental evaluation. Also, if a schedulable partitioning does not exist or cannot be found by this FF-based heuristic, then we fall back to global IDF. And also, we have to keep in mind that Apdf is not work conserving, so we may leave cores idle while there are tasks ready to run but not yet scheduled on a CPU. So we designed a variant also called A2PDF, which also adds an adaptively pull operation that kicks in when a core goes idle. So in that case, we pull the non-executing task from overloaded cores with the most urgent deadline. We pull it on the current core that just went idle. And but this operation is only done if the source core was actually overloaded in terms of the Llewellyn Island test. So again, the general properties of A2PDF are still that we try to recover a minimum of work-conserving property, but that's only used in those situations where we didn't find yet a suitable placement of our tasks. Again, once a schedulable partitioning is found, though, then no more migrations happen, so tasks are not moved again. So again, this scheduler is not work-conserving either. So the schedulability of Apdf can be easily analyzed by applying the Lopez and Garcia test from Euromicro 2000. And let me skip about this. Just highlight that the first-fit invariant in Apdf is not strictly enforced. So there may be times due to the dynamicity of the task set in which we don't really satisfy the first-fit invariant. In terms of implementation, again, let me skip the details, but it's just want to highlight that the major places where we modified sched deadline are fundamentally in the select task run queue, which is responsible for choosing a proper run queue, so a proper core where to deploy a task in 3 cases where a task wakes up, or when we do an exec, so we are running a new program, or when we create a new task after a fork, clone, pthread create, etc. So the other places are the push and pull functions, which are called by the core.c general framework, and we modify these functions as well. So more precisely, we basically let the select task run queue, push the alt task, and pull the alt task. These 3 functions in deadline.c have now become 3 wrappers that are calling either the original functions in sched deadline or the new functions that we provided for implementing the first fit or the worst fit allocation heuristic, which rely fundamentally on these 2 CPU find functions that, instead of using the global heap included in sched deadline in CPU DL find, they actually scan through the CPU linearly by just checking on CPU after one another. The actual scheduling policy under use with our modification can now be changed dynamically by writing into this sysctl proc tunables. So we can choose between the original global IDF from the mainline kernel, or global IDF, or as I said, it can be configured in a number of different ways, or we can actually use this APDF heuristic with the first fit or with the worst fit. And also the fallback to global EDF is an option that can be selectively enabled, as it is also the A2 PEDF variant. So the adaptive pool can be enabled by using this dedicated entry. Let's get to the experimental evaluation. So in our experimentation, we tried to run randomly generated task sets using RT-App on Linux, and we ran it on 4 CPUs and 8 CPUs configuration, simply to compare these with the corresponding simulations we had made for SAC 2020 paper of last year. So here on top you can see the simulation results. On the x-axis there is the total system utilization in terms of real-time tasks. On the y-axis we have the percentage of deadline misses in log axis. You can see that global EDF, as from the simulations, has quite a number of deadline misses which instead are not present when using already the APEDF. However, while in simulation the APEDF reaches global EDF curve and goes even a little bit worse with very high utilization, then the A2 PEDF actually recovers. So the little bit of work conserving properties of A2 PEDF actually recovers the situation in the highest utilization. So it is consistently lower than the global EDF curve in simulation. If we look at the real experimentation we obtained again on a 4 CPU system with 16 tasks, same condition, what we have is that here in this picture, the plots and that are missing, the dots that are missing are due to the fact that we had 0 deadline misses. So as the y-axis is in log scale, you wouldn't see that. So basically for low utilization, we have a very similar behavior of all of these 3 policies with a little bit of noise. And the only interesting part is the very high utilization side. So we have between 3.6 and 3.8 utilization of a 4 CPU platform. So in this case, we can see that APDF simple without pool actually ends up by behaving a little bit worse than global EDF in terms of deadline misses. But the A2 PEDF also is again a little bit better, but still it's not so better than global EDF as we had simulation. You have to remember that in our real experimentation, real-time tasks cannot have an execution time that approaches too closely the worst case execution time we are providing in terms of runtime for under the deadline scheduler. So while in simulation we could simulate tasks whose execution time was getting exactly equal to their theoretical worst case execution time, under which this utilization is computed. In the case of the sched deadline real experimentation, basically the system is always a little bit of a provision, in the sense that the actual execution times are a bit lower than the worst cases that are actually equal to the runtimes that have been given to the scheduler. So that means that we have slack. So global EDF has a lot more chances to actually recover and avoid deadline misses, which is what happens here. Now we can see instead that if we look at the migrations, average migrations that we are seeing, it's not per task set, it's per job. We can see that in the case of our APDF scheduler, we actually have no migrations at all, even up to very high CPU utilizations, and this is perfectly in line with what we had also in simulation. And on the other hand, global EDF, so the original sched deadline with its default configuration, just keeps migrating tasks a lot. As you see, each task undergoes 1.25 migrations during the run. So in this, on average. So we repeat the same experiment on 8 CPUs. Here, the system is a little bit more complicated. We have 8 CPUs up to This is an example with 16 tasks and various utilizations. Anyway, we tried up to 25 tasks in the paper. So you can see that from this plot that, for example, in this case, Apdf and A2PDF are doing, in terms of deadliness ratio, pretty well similar to global ADF at, you know, mid to high utilization values. However, for very high utilization values, here from 6.0 to more or less to 7.5 and to 8, 7.8 should be. So in this case, we can see that the A2PDF curve is actually consistently better than both the other ones. So particularly it's better than global ADF. And remember, we have a log scale deadliness ratio axis here. So again, we are having a good benefits in terms of deadliness ratio, but especially we have a huge benefit in terms of average migrations that are really small in this case. And this is again in line with our simulations. So to conclude, we propose the Linux implementation of adaptive partition EDF, which is available and released as an open source patch. You can access it here. We presented experimental results with 4 and 8 cores under various utilization and task configurations. We discussed the obtained results. Let me add that we measure the overheads, that is below 3 microseconds, for the execution of the placement first fit placement logic. However, we have to observe that Apdf mostly skips task relocation decisions, because once it finds a suitable schedule, so a partition scheduling, it will never really search anymore for other CPUs. So on the other hand, SchedDeadline keeps consulting and querying the global heap in that CPU find function to continuously try to double check whether the global ADF invariant is still holding. So this is to say that in the end, the overheads turn out to be even, you know, significantly lower on average than SchedDeadline. So future work, we plan to improve the patch set, making engineer it a little bit better. There's a number of open issues in the code, but if you want more details, you can write me. We plan to experiment with data-intensive workloads, where we should be able to see more clearly the advantages of the new schedule in terms of migrations, of your skipped avoided migrations compared to global ADF. We plan to enrich the scheduler with an energy-aware scheduling policies, so integrate with the EA's framework and play with DBFS frequency changes on mobile platforms, especially Android and AMP Little or dynamic platforms from ARM, and double check whether we have an effective an effectiveness also in terms of energy saving. This is a list of our related publications, and thanks for watching. If you have any question, feel free to write me.